let's reblock the machines. Okay. And thanks for computing. And take it away.
Take what I wanted. Okay, good. Okay, hi. So my name is Oren. This is going to be a pretty machine learning heavy talk. I hope you will survive. I know it's not your usual thing. So obviously I'm an AI researcher. And engineer. What you just saw here is a 3D animation, which should be running. It should be an animation, but never mind. That I created. For the past 2 years, my main hobby, if I'm not doing machine learning stuff, it's been 3D modeling. And I'm going to talk a little bit about that today and the project that I did that involved. If you don't follow the exact specifics, that's fine. You can ask me later. I think the overall architecture of the system, I hope, will be inspiring to some degree. So for my 3D modeling, I'm using a software called Blender. It's an open source software. Anyone can download and use it. And I find it just completely fascinating. It's like a whole world that you can move around like this, and you can take a cube or any kind of object and edit it and make any kind of world that you like, which is a lot of fun. I'm not going to talk about the geometry of like moving the structure of the cube so much, but if you can see on the left here, we have something that's called the shader editor or the texture editor. And over there, I can like change the color of the cube. But more importantly, what you can see me doing now, I'm building this sort of graph over there. And you can see I put like a node in between the left side where I have the object coordinates and the right side where I create the actual colors. So what I'm doing here is basically mapping the coordinates of the cube, of every point of the cube. So every point has a coordinate, the x, y, and z coordinates, and they're going to be mapped to a specific color, and that's the color that we see. So the node in between, which in this case is called Voronoi texture, is basically just a mathematical function that takes in a vector, a three-dimensional vector, and outputs a three-dimensional vector, three-dimensional because color is also three-dimensional, red, blue, and green. So if I can create this kind of structure, if I have nodes, if I have these functions that map three-dimensional vectors to three-dimensional vectors, I can start creating an interesting tree of functions. And I have different kinds of nodes. So this one is called noise texture. It's just a slightly different function. It creates a slightly different texture there. It has different parameters that you can play with. And I can input the output that goes from one node into another. And then I can have maybe a tree that goes from the coordinates into noise, into this Voronoi thing, and then into the color. I'm starting to get all kind of interesting textures. So that's a whole field that I'm not going to explain in detail, but I find it fascinating. What you should be taking from this is just that in Blender we can build these procedures of graphs that are basically using primitive functions, and we can sequence them together and build this tree that represents a procedure that generates from coordinates, generates colors basically, or any kind of textures. And if you're an expert in this, you can do really cool stuff. Like this is just the kind of lava cool thing that I did. And it's not actually that big. You don't need so many nodes. This one is supposed to be like a wood texture, and you can see it's just like 4 nodes. When you understand what you're doing, you can do pretty much anything. You can do like really realistic textures, building their procedure. And for me, this becomes a lot of fun as an analytical person. Once I started learning these things, I just like walk around in the world and I see, okay, this is like a carpet, interesting. Maybe it's like a combination of like this kind of node with that kind of node. So I start looking around me, and it becomes this exercise in deconstructing the textures that I see of the wall, the floor, and trying to figure out from a texture that I see from an image, what is the procedure that's behind it? What is the analytics that goes behind it? And then ideally, if I can do that, then I can create a texture that resembles this. And if you're a professional in this, you can create really realistic textures. And as a data scientist working with AI, my immediate thought then is, can I make a model that can do this? Can I make a model that takes in an image, a texture, looks at it, and says, oh, I get it. The procedure that makes this texture is that. Now, why would I want to do that, by the way? If I already have this software and I have an image, why not just put like the image on this sort of cube or something? So procedural textures have a lot of advantages. Firstly, they're like infinite resolution because it's just like a series of functions. You can always zoom in and see all of the tiniest details in the wood. It's like an SVG, so it's infinite resolution. Obviously, compression is an advantage because you can imagine in just a few lines of text I can describe that wood texture that we've seen. So, I mean, it's a tiny file size. And you can generate loads of variations because if you have like different seeds for random values, you can play with them. You can play with the parameters, with scale, with whatever. So these are a lot of advantages to converting images to procedures. But zooming out just a little bit, I'm going to be talking about this model that I built to generate these procedures. But zooming out a little bit, what I'm trying to accomplish here is called program synthesis, which is the process of automatically generating computer programs or procedures from high-level specifications or from several examples. And that actually has a lot of different uses because you can describe a lot of problems in terms of these graphs that have primitives and you just connect the inputs and their outputs. Lots of puzzles, if you're familiar with the ARC puzzle, it's a very famous machine learning exam for AI. That can be described as that. Fitting mathematical equations, if you have inputs and outputs and you just need to figure out what are the mathematical functions that you put in between. Code in general, any kind of computer software can basically described as these primitives that we just connect their inputs and their outputs. Building electric circuits, anything like that can be described as program synthesis. So if we can create a model that does program synthesis, we potentially can solve a lot of different problems. So this approach of program synthesis is useful when we have a lot of these small components transforming inputs into outputs, and together they create a ridiculously huge search space. Because in Blender, as you've seen, there are tens of different primitive nodes. Every one of them has a few parameters, some categorical and some are numerical. And you can make like an infinite number of tree structures. So the search space is ridiculously huge, and you can really make any kind of texture. But once we've made one, verifying the solution is relatively easy. You can just check if that's the same texture. So if you have all of these conditions, program synthesis could potentially be useful. And that's kind of in a sense, the holy grail of AI, because to have a model, an AI that can look at something and actually analyze it, not just work like these black box models that we have today, like LLMs, but actually analyze something and explain this is the procedure that is building this, it's super useful and gives you a lot of explainability. Okay, so that's the problem that we're trying to tackle today, and I'm going to explain what I did to approach this. So basically, we can think of this problem as a machine learning model from image to this sort of Blender tree. Or in other words, an image to text model. Now, why is it an image to text? Because I can take that Blender tree and convert it to text. Not going into too much detail, I created this sort of small language just for myself, which has these two components, the nodes and the edges, and the nodes describe the nodes that I have in the tree and the parameters that each of them has, and the edges describe the connections between them. And now I have this text that basically describes the procedure that we've seen there visually as this sort of tree. So now my problem is really a problem of image to text. And I have more tools to solve image to text problems. So firstly, to do any kind of machine learning, you need a data set. So I created the data set with about 100,000 images, randomly generated textures that I generated in Blender. I'm going to talk a little bit later about how I generated these images, but I have 100,000 images that I created, and for each image, I know the corresponding text, the procedure that created every one of these textures. So by the way, all of the examples here are grayscale, but the same principles would work for color. I just wanted to, for simplicity for my project, I wanted to make it a little smaller. So how can we do this? If we have these images and we have their text, how can we convert the image to text, the image to procedure? Well, I assume you're familiar a little bit with large language models and such, and how they function. Generally speaking, there's a Lego block, we can call this a decoder. It's a kind of transformer. Not going into all the details of what's going on inside of it, but generally it takes in words, converts them. This is called like an embedding layer. So it converts the words or tokens into a sequence of vectors that try to represent the meaning of these words in vector form. They go into a decoder, and the decoder outputs one word or one token. And then this happens repeatedly. So what can we do if we want to create not text to text as we usually have with LLMs, but image to text? We need to take an image and convert that into an embedding, which is pretty simple. And I'm not going to go into the details, but if you've ever done a bit of machine learning, there's something called a convolutional neural network, which basically just takes an image and converts this, extracts the different features that the image has, the different elements of the texture, and converts this into a vector. And then when you put this into a decoder, it outputs a single word from the text that you want to generate. And then you take that word or the token and you put that back into the decoder, and you generate the next word and the next word and the next word until you have the entire text. And that's how LLMs work generally. They just create words sequentially, one after the other. And this should work relatively same way for my model. So I have my images, my 100,000 examples. I have a model. I just need to train it. It's not a huge model, just about 112 million parameters with my 100,000 examples. I trained it for about 4 epochs, which seemed fine, and the lost plateaued after that. And now I have a model that takes an image and converts it into a text. So how well did that do? Well, I gave it this image, and it created that, which is cute, but not what I was going for. I gave it this image and it created this, and again, you can kind of see that it sort of extracted the idea of like rings, but kind of missed a lot of the detail. Sometimes it got a lot of the basics right, but it missed like a whole big chunk of it. Sometimes I don't know what it was doing at all. So why is that? Well, it really makes a lot of sense, because as I said before, you have a ridiculously huge search space here. It's not really reasonable to expect a model to hit it on the first try. You wouldn't even expect a human to do that, right? When I try to create textures, I don't like blindly code this and build the whole thing and say, oh, now it's going to be perfect. No, as you do with code, you're probably adding a little thing, testing it, seeing what is the result, seeing, oh, I need to change this parameter a little bit, and you are flexible to what you see. You respond to it. You don't code blindly. And I think a lot of intelligence is really about that. It's about responding to the environment and being flexible to what you see and making these adjustments. So maybe what we need, and this is the idea that I came up with for this project and I found interesting, maybe what we need is not so much a model that tries to solve a problem. Maybe what we need is a model that learns how to search for a solution. So we need a new architecture, an architecture that allows us to look for a solution and, given one state of this Blender program, see what can we do to go in the right direction and not so much find the solution directly. So before I'll talk about the architecture of this model, I want to talk about my data set generation. I said before I generated 100,000 images, these textures, so I want to talk about how I did that. So basically, it's a pretty simple procedure. I start with like an empty tree, an empty graph that basically just maps the coordinates of this cube thing to the color, so you don't really get anything. And then I can randomly select one of those primitive nodes that we've seen. So we had these Voronoi, and we had the noise, and all kind of stuff. So I just randomly add one somewhere here. And now I have a new texture. And now I can say, OK, let's add another one randomly, maybe on like that edge over there. So I add it, and OK, now I have a new texture. And now I say, OK, let's randomly not add a node, but let's change a parameter in one of these nodes. And I get a new texture. And what I'm doing here is not only creating different textures, but creating a network of textures. So now I have this network of these different textures that I created. For each one, I know the procedure that generated it. But more importantly, for each one, I know how to get to any other one. I know that to move from one of them to another, I need to add a node or remove a node, and where exactly I need to make that adjustment. So slowly, I'm building this network, which has 100,000 different images. And I'm building this knowledge of how to move across this network. So now with very basic search algorithms, I can say, OK, if I'm starting at this point, how do I get to that point? How many steps that's going to be? That's all knowledge that I have. So generally speaking, what I did 10,000 times is randomly started with like an empty tree, randomly decided how many steps I'm going to take between 5 and 15, and then at each step randomly either added a node, removed a node, changed the parameter. There's a short list of actions that I can do. And now I have my data set, which again includes images, procedures in text form, all the connections between these textures and procedures, what are the changes that I need to make, and the distance really between any 2 points, which is going to be helpful also. And my goal is to create an AI, a model that knows how to traverse this network, that knows how to walk on it. So if I tell this model, you are starting over there with this empty texture, and your goal is to end at the target, what is the one move that you need to make? And ideally, it will give me the right move, and then I can make that move over there, and it will tell me the next move. So we almost have everything. We know how to input images into a machine learning model. We know how to input the text that describes the procedure. What we need to figure out is how do we get the model to tell us what is the action that we need to take. Now, we can do this like an LLM that just writes one word after the other, but that's going to be very slow, and lots of reasons why I won't do that. So instead, we need to find a clever way to encode actions, to encode edits to our tree. So how can we do that? Well, if you think about it for a second, when I have one of these Blender trees that are procedures that create my textures, any action that I can take here always happens on one point on this tree. So maybe I'm adding a node over there, or maybe I'm changing a parameter over there, but it's always on one specific location. And in the text form as well, maybe, okay, you can hardly see it for some reason, but there's text over there. Maybe I'm changing a specific token there or another. It's kind of weird. The point that I'm making is that every edit is relevant to a specific point, and in the text form, it means a specific token in a specific word, you may say, in my text. And every edit is a discrete label. I'm either adding a noise node, a Voronoi node, one of those primitive nodes, or maybe I'm changing a parameter, but there's basically a closed list of 60 or so actions that I can take, and any of these actions can appear in any location on this whole graph, on this text. And this means that what we're looking for is a token classifier. Because basically we want to find out which token needs to take which action. So this is the architecture of the model, and it's not as bad as don't be alarmed, it's not that bad. Basically the bottom here is the inputs, so we already know all about that. Okay, we know how to take images and put them into a CNN, which creates these embeddings, which are just these vectors, which we can put into machine learning models. All of the text here is just the text that describes my procedure, as we've seen before, and I embed this, and I put this into an encoder, which is very similar to the decoder that we've seen before, except that an encoder doesn't output just like one word. It outputs a series of labels for every one of my tokens. So if I have a parameter in one of those nodes that I need to increase, it can say, okay, you need to increase that specific one, because every one of my tokens in my text gets a label of its own. And if I give it another example with like another texture, it will say, okay, here you need to add a noise node or something like that. Again, it's pointing to the specific, you should be seeing text here, to a specific point in my text, and says this is the point in the text that you need to change, which corresponds to this is the point in the tree that you need to edit. Now, technically, it's not really giving me just one label. It's giving me all of the probabilities of every label for every point in this, on every element in my tree. So it's taking, the encoder is a classifier for every action that you can possibly take at every point on the tree, and gives you a probability for every one of these actions. Additionally, quite conveniently, as I said before, because I know from my data set the distance between the source, where we are now, the state that the Blender is now, to the target, I can use this in my model. I can convert the number that I know, like 3 steps away, to some number between 0 and 1, which represents how close I am to my target. And I can add that to my model. It can also output a value estimate of how close am I. So in short, I can train a model that takes in a tree. I go to this model and I say, here's a tree, this Blender tree, here's a procedure, and this procedure makes this texture, and my goal is to make this texture. And please, may you model, tell me what is the one move that I need to make, what is the edit that I need to make to get closer, and also tell me how close I am. And this model actually gives me not one edit, but the probability of every possible edit that I can make. Every possible action, I get the probability of this action. So because I have this data set, I can train a model like that with this architecture. This was a similar model in size, but I have way more examples because I only had 100,000 images, but they're all connected. And now each example is a starting point and an end point. And with 100,000 images on this network, I can sample way more than 100,000. Every endpoint can have lots of different start points and so on. So I'm actually sort of squeezing more out of this lemon. From the same set of examples, I'm creating way more examples to train my model, which I think is pretty nice. And now we're almost there, basically. I start with a texture, this empty graph with like no procedure. Think of it as like an empty Python or Elixir code with nothing. And I give it the target, and I ask my model, what should I do? And it gives me this list of suggestions. And with this, for each suggestion, it gives me the probability. Now I can take these probabilities and create their textures. And I can also put these textures into my model and get a value estimate of how close each one of these is to my target. Now I need to sort of decide how I'm expanding my network, because I can't actually go in every direction that the model is suggesting, because there's like way too many directions. That'll be basically like trying to brute force this problem. So I need to pick only a few options. So one way to do this would be greedy. Let's just pick the top, the one with the highest probability, or the 5 with the highest probability, and take them. Often in machine learning, we like things that are a little more probabilistic. So another option is to sample the actions proportional to the probability given, but this also allows sometimes for the lesser, the options with a lesser probability to get sampled, and that sometimes is helpful as well. I went for a third option, which I'm not going to explore in detail, but it's called Monte Carlo tree search, which is a very clever tree search method that balances exploration and exploitation. And this is something that was used in AlphaGo, if you've heard about this. This is basically the tree search algorithm that is used to create the best chess players, the chess engine, and Go engines, and so on. Which is a clever way of trying different directions, but also not trying them too much, so you don't get stuck in like one direction. If you gave it a chance and it didn't produce anything meaningful very quickly, you go in another direction, then you can come back to that one. So it's a complicated algorithm. I'm not going to explain all of it, but I really like the idea of using the same algorithm that is used for games, because I like this as a metaphor, because you're kind of making a move, and then you see what the world responds, what your opponent responds, what happened after I made this move. Oh, okay, now the texture changed this way. Okay, so what is the next move that I make? And also you sometimes need to have this long-term thinking. Sometimes you need to sacrifice your queen. I make a move, it doesn't make the texture look so good immediately, but I know that 3 steps along the way it will work. So the same kind of tree search algorithm makes sense, I think, for this problem. And that's pretty much it. We have our texture. We create a bunch of possibilities. We sample them with this Monte Carlo tree search. It could be this random sample as well. And then we follow these directions. We create more, and we create more, and we create more. And slowly we're expanding our network of possibilities. It is a little dumber than me, I guess, because I don't need to create loads of different textures. It's a bit brute forcing it. But it's doing it very quickly, and it is making these very educated guesses. And because I'm using the encoder, as I've shown before, that gives me a whole list of options at every point, this is very fast. I can make, in like a few seconds, I can make hundreds of these possible textures and like move in all directions and look for the possible solution. So my whole program synthesis model is this. I start with the empty texture, and for about 20 times, I give it to my edit encoder model that we've trained. I do this until I have a few hundred options, and then I select the best result. And these are some of the results. That's the input that I gave to my program synthesis, and it gave me something that I think is pretty good. It's not exactly the same image if you look at it, but it is the same texture. It really figured out how to make this procedure. And obviously, I'm not just getting the image, but also the procedure that made it. For this image, it gave me that. Not bad. This one is like almost identical. And I want to show you, this is not what it gave me. I just want to show the process. So this is like the image that it starts with, where it just maps the coordinates into the colors. And then if you follow the path that it took, it would, is that moving? No.
Does it need internet to play?
Oh, there we go. Yeah. But the projector is not amazing. But OK. Well, ideally, you could have seen that it's slowly moving in the right direction until it reaches a similar texture. Can we do this again? Yeah. OK, yeah, you get it. So if I follow the path that it took until it got to the actual texture at the end. So these are all textures that I generated automatically with my procedure. So they're a little easier for the model. When you go to these very realistic textures, those are a little more complicated. But I think, again, compared to what we had before, the model that tries directly to get to the solution, to the procedure, my edits encoder that works and slowly gets there and makes these little adjustments, works much, much better. And you can see that it's fine-tuned. It gets that grainy detail that the image to code encoder that tries it in one go really couldn't get, because it didn't like see and then say, oh, I'm missing this one element here, let me add that thing and let me change that parameter. So to sum up this whole procedure, I randomly generated a data set of these trees and their textures and the connections between all of them. Now I can sample a data set of starting points and endpoints and train a model that takes any point, any state in my program, and the texture that it generates right now, and the target texture, and outputs the suggested actions that I should take and the value estimate of how close I am to the target. And now I can iteratively sample, expand my network using Monte Carlo tree sampling or a similar algorithm until I get a result. And I think this is a much, much better approach. Especially when you have a huge search space. Don't create a model that learns, that tries to solve a problem directly, but one that learns how to search and improve on previous solutions, and let this model see what it's made so far and respond to this. And when you do all that, I don't think program synthesis is completely solved. That would be truly the holy grail of AI. But you can create a procedure that gives you this smart search, which sometimes can get you far enough even in a huge search space. So that's it. Again, my name is Oren Mata. If you want to connect or ask me questions later, that's my LinkedIn. Yeah, thanks. I hope that was clear.
So, who wants to go first with a question here?
Yeah, so this is really cool. I'm curious if you tried different pre-search algorithms besides the Monte Carlo one. Is it just like the one you tried?
Just the three, like the greedy.
Okay, so you didn't try.
I did try the other two. Yeah, I tried the greedy. I tried the random sampling, like proportional sampling, and the Monte Carlo. And I mean, they all work to some degree, but the Monte Carlo was clearly the best. Yeah.
Cool. And also, similarly, I was wondering if you tried some kind of vision transformers instead of CNNs.
Yeah, so I didn't, although I know they're more popular right now. I think there are reasons, like if I had infinite amount of time, it would make sense to also try that. Why not try all the different options? I think particularly for textures, it just makes more sense to me to use convolutional neural network because of the way that they work. Because they're basically extracting features, these small level features, they're extracting the texture. So it makes sense to me that they would create a vector that every element represents whether or not there's a specific element of a texture. And that's not exactly how vision transformer works. So it made sense to me that this will work better. So, yeah.
And finally, sorry, so many questions, but it also seems a little similar to something, or like the problem could be both similarly to something like Clip, where you put like the image and text in the same medic space, and, and I was wondering if that's something you considered, or you just like went for this.
So it is quite similar to Clip, but I mean, the end it is just fine details of the architecture and the fact that I'm not, because in Clip you are not trying to slowly approach the solution. Right, You're just trying to generate the text. So Clip, in terms of architecture, is quite similar to the first model that I tried. I think there's some fine details there of why it's different, but basically it's the same. Yeah.
Cool.
It uses vision transformers, for example. Yeah.
Wait for me, so people on the screen can also hear you.
Thank you very much also for the talk. Really amazing stuff. I was just wondering, in your search, are you purely forward searching or also backward searching? I mean, you can also set the goal as your source and the plain shape as your target, right? And do a backward search of reducing noise and so on, and that would probably, that really constrains your search space. And normally, if you go backward from your goal towards
Coming in, like the problem that I have is like I need to create a texture. You're saying if I already have a texture and I want to like remove something from it, or like
If you take, for example, this image of, a real world texture that
Yeah.
you want to get the graph for, right?
Yeah.
One of those. I mean, this is just a texture, right? You can use it as your source and ask the system, what do I need to do in order to produce
a different texture.
of nothingness?
Yeah.
Right, and that way you would go both ways at the same time. You can, or
Yeah.
not at the same time, but you can actually have a measurement of distance removed between steps, and once you're done, you immediately have the full path.
Yes, but what I don't have, when I trained the model, it did train with every kind of directionality because I sampled from my entire network. I randomly sampled starting point and end points, and I think I did bias it a little to start from like an empty state because that's what I wanted to solve in the end. But I did let it sample from any kind of start and end point. But when I'm actually trying to solve something, if I have the texture, that doesn't mean that I have the procedure that makes this texture. So I have to start with an empty when I'm predicting, when I'm trying to generate something. I only have an empty state unless I created the procedure.
But isn't it, in a way, arbitrary? What is your source and what is your target? Either you remove more and more noise and you remove more and more nodes to get to the base texture, or you add them, right?
Yeah, but if you give me the input here and you just give me the texture, I don't have the corresponding procedure, that Blender tree that makes this texture. I need to make it first. That's the problem. After I made it, then you can say, okay, how do I move from here to like something else?
We can discuss it later.
Okay.
Interesting question.
Did you want to
Yeah.
ask a question or?
No.
Actually on. That's a great idea. That's a great idea. Actually, it reminded me, like I was working on routing, like like Dijkstra. There's this idea of doing Dijkstra from both sides, basically, right? And if you do Dijkstra from both sides, the start and the end, you can actually get with fewer steps to the resolution.
Mm-hmm.
But with that said, enough of routing. More questions on LLMs? Or like, actually, this is not an LLM. There was actually a question I wanted to ask you, whether you feel like there's, are you seen as a heretic, like from the LLM maxis, or is that something that, because I think you said like two or three times, like, but you don't need an LLM, you can do it this way.
Yeah.
Is that something you perceive, or you feel like, what's your opinion on that?
I also tried using an LLM directly. So you can put an image into like ChatGPT or something. And I did try this. I gave an image of one of these textures to ChatGPT, and I said, can you create the Blender code? Because Blender is connected to Python, so it can create this code that just generates this kind of Blender tree. And it didn't work very well. Actually, I have some I have the examples here. I didn't get into them. But you could see that it's sort of figuring out like generally what it needs to do. So, it stops sharing. How do I? Okay, never mind. The point is, it kind of figured out, okay, I want to have these like sort of cells, but it really didn't do a very good job. That's for like directly using an LLM that was never trained on specifically this task. Generally speaking, I can say that I'm not, I don't know if a heretic, but I'm not a huge believer in LLMs and their potential to become AGI and like solve all the problems ever. And that's kind of what I value in this sort of model, that it's trying to give you explainability. It creates a procedure. The goal of this model is to be analytic, and in a sense, it's more intelligent, I think. Because this is what I do as an intelligent person. I look at something and analyze what's going on, and that's what this model is trying to achieve. So yes, I'm taking a slightly different route from LLMs. All credit where it's due, that they have their advantages, but I think they're also very limited sometimes. And I think these kind of models can be helpful. But again, it's the same building blocks. Like LLMs use decoders and encoders and all the same building blocks. They're just like trained on the entire internet and are huge models. And you can see that a relatively small model here was able to beat any LLM because it was specifically trained and is making these small adjustments.
That's amazing. Any more questions? What hardware did you use for training? Did you just train it on your machine there, or like did you train it in the cloud, or?
Yeah, partly on my machine, which was good enough because I do have a GPU. Because I'm doing, luckily enough, my two passions also both use GPUs because 3D modeling, rendering needs GPUs and training models. So I have a nice GPU, so I trained this, but also just Google Colab was the most convenient one to train. Yeah.
Thank you so much. With that, let's take a short break, get some quick drink, and then we will relatively quickly come back here, and Maciej is going to take us even deeper into the dungeon of machine learning.
This is a nice microphone.
Yeah, they're nice.
Green means it's good.
Nice, thanks.
Green means it's good.
That's what I thought. Well, so let's get started with the second part. And Maciej is going to tell us more about Esmeralda. So first I mixed up topics here, because usually it's Chris talking about Esmeralda, but actually there's some really interesting story here. So with that,
Yeah.
please give a warm applause to Maciej.
Thank you. So yes, thanks to Chris for giving us the ammunition to talk about. We are going to talk about distillation, but not the kind of distillation you might have in your mind, about distilling AI models. And we're going to use Esmeralda as an example. So if you've been here last week, you've seen Chris explain what Esmeralda is and how it works. So I won't cover that much, but I will show you how you can use distillation to make something like Esmeralda work with a model that's smaller and cheaper to run and faster and so on. So that's the idea. Where does the idea come from? Yes. There is going to be some. There's going to be some stuff that I'm showing, but much more raw than what you might expect. Yeah. So distillation is something that's pretty well known in AI community. One of the sort of most well-known papers is this one from 2015. You might have heard of Jeff Hinton and Jeff Dean. Like they're pretty well known, but they had this paper, and it's not the first one that did it, but it's kind of the most famous one. And the idea of this paper is how to take in this case, that's an ensemble of models. So if you've ever done or looked at like a Kaggle competition where the idea was to classify something well, for example, most high performers were ensembles, which means that it was not a single model, it was a bunch of models, and they were voting together, and in the end, the result of this averaging was your answer, and that kind of gives good results. But it's kind of a pain to run an ensemble of models. Instead of one, you have to run multiple, and it takes a lot of computational power. So they came up, or they sort of implement this idea of distillation, where they use this big ensemble or a teacher, and use it to train a much smaller model to do the same task in a better way. And the funny thing is, like, if you open a computer science paper and it starts talking about insects in the first paragraph, it's a good one. But basically, the idea is that larvae are optimized for some stage in their lives, and then they transform into beautiful butterflies, and they have very different constraints, and like they're differently adapted to the thing they need to do at that time. So they're making the argument that models should be the same. There's the training part, which takes a lot of power and needs to be needs to extract a lot of information from the world. But then once you have a model that's trained, you can exploit it using something much more efficient. So that's basically the idea of what distillation is. And where's my cursor? There we go. As you can imagine, like it's been more than 10 years since this paper has been published, so a bunch of work has been done. But a lot of people are coming back to this because nowadays you can build a lot of cool stuff with AI, and when you want to make AI do something in the real world, you start building an agentic system, so you have tool calls, and you end up usually with sort of a graph of nodes, something like Oriol was showing, but each node, instead of producing a texture, would like call a tool or do a web search, and then some other node would take that as an input and do something else with the result, and so on. So you end up with this bunch of boxes, and each box, when you start building it, it's usually an LLM, because that's the easiest thing to get started. So you use Claude or ChatGPT or whatever, and then you get something that works, and then you realize that running it is very expensive and it's very slow. So then you start thinking, okay, how can I replace individual boxes with something that maybe is a little bit cheaper? And the idea is that you start with something very general, very powerful, but then once you nail down a narrow domain where you want to perform a specific task, you can start thinking about replacing it with something that works just as well on this narrow task, It doesn't generalize as well, but it's fine, because you just want to do this narrow task. And it just so happened that NVIDIA published this paper, Small Language Models Are the Future of Agentic AI. And it sounds like the kind of paper that the company I work for would write, but we didn't write it. In fact, NVIDIA wrote it. So the company I work for is called Distill Labs, and as you can tell, we do distillation. We basically try to take all the literature that has been created about distillation and turn it into a product that's easy to use. So anyone can read the papers and implement it, but it's, takes a while, so we try to make it easier. And what NVIDIA is arguing in this paper is that over time, more and more people will start looking at efficiency much more than today. Because there is this, right now we're still kind of looking at capabilities and we try to get things to just work, but once they work, you start thinking about how to make them cheaper. And that's basically what they're saying, that over time, more and more people will look at small language models, large language models to implement these sort of specific tasks. So with all that intro, we're going to use Esmeralda as an example, and I'll walk you through how we can take a model that Esmeralda uses and then distill it to get something else. So just so everyone is on the same page, I don't know if you've been here last week, but this is Esmeralda. Chris and the team built it, and you can go to esmeralda.chat, and then you can ask, if I have internet, you can ask questions about Elixir libraries. So let's ask, I'll just pick a first library as JSON. How can I convert Meetup to JSON? And then Esmeralda will do a bunch of things. So there's a whole talk last week. If you missed it, there's a recording somewhere. But basically, Esmeralda has looked at docs for different Elixir libraries, index them, vectorize them, put them in a database. And when you ask a question like this, it looks at all the data it has about the specific library, about the code, the source code, and the documentation, and then pulls out relevant chunks of that documentation and then produces an answer based on it. And you can see that, it tells you how to do the thing. And you can ask print anything about any Elixir library and it will give you an answer. So that's how it works. And how can we make it run differently? Well, so first we think about the problem that we want the model to solve. And this is, again, going to be sort of with apologies to Chris, I used, so what I did was I checked out the Git repository, so Esmeralda is open source. I checked it out, and then I asked Claude, hey, can you look at this source code and give me a system diagram of how this works? So this is going to be the result of that. And I'm sure there are things wrong with it, but I think it sort of gives you a nice overview. By the way, this is JS, so Claude just produced this one shot, so who knows. But it did look at the code. So basically what happens in Esmeralda is the user asks a question. There is some library stuff that, for today we won't care about that. The question gets vectorized. So there's, the whole embedding there. So we end up with a vector representing this question. Then we do two kinds of search using this query. We do semantic search using the vector, using vector similarity. And we also do full text search. From each of those results, we get a bunch of, from each of those kinds of search, we get a bunch of results. Then we do fusion, so we sort of put them together into one set of results. Then we take all these results and build a context, which is basically a bunch of text telling the LLM, hey, here's a question I want you to answer. Here's a bunch of information, and now produce the answer. And then we give it to an LLM, and it provides an answer. We are going to be running a local version of Esmeralda, so we'll use Olama, which is sort of a server that you can use to run LLMs locally. But there are other options there too. And then, streaming, and then you see there's the answer. Chris, how accurate was this? Amazing. Okay, cool. So no major mistakes. Good. So given this, what the model gets is this. So we're going to keep all of the system static, and the only thing we'll